Hi everyone, welcome to lesson 2 of the fluids chapter. This lesson is on Pascal's principle. In this lesson, we will use some of the information that we learned from lesson 1, and we will state Pascal's principle, and most importantly, we will learn how to apply Pascal's principle to talk about something called the hydraulic press. So to get things started, Pascal's principle, just stated, is changes in pressure at any point in an enclosed fluid at rest are transmitted undiminished to all points in the fluid and act in all directions. So that's a bit of a mouthful, but we'll try to break it into pieces and understand each part of it. I think the key point is that if I had to highlight some key things for you, it's that pressure can be transmitted through a fluid. So we can actually, I'm going to try to draw a little device here. I'm going to draw a U-shaped object that holds some water. Let's actually erase this. So imagine, if you will, a U-shaped object that has some water in it. We learned in the previous chapter that water will, or the previous lesson, excuse me, that water will reach its own level. Imagine at the ends of each of this U-shaped device, we put a little plug so the water can't escape. And what Pascal's principle says is this, so these are like those stoppers. If you apply pressure, let's say on the left-hand side, pressure here, pressure number 1, that pressure will get transmitted through the liquid and be applied to all points of the liquid. And in one instance, it'll actually apply a pressure up on the second stopper, and it will actually cause it to lift. Now this isn't that interesting when these are the same area, because pressure 1 is going to equal pressure 2. So if I push down with a force of 1 Newton, I'm going to get it pushed up with a force of 1 Newton. The interesting thing comes into application when we change the areas of these two things. But the key right now is that the pressure is transmitted through the fluid. If we change the area, changes in pressure will be the same, even if the area changes. We can multiply the forces. So I'm going to modify that U-shaped device that we're imagining for a second. And it's going to look something like this. We're going to start off with a smaller, and then the second part of the U-shaped device is a bigger area. So let's say now that we place those rubber stoppers smaller here, and we have a larger one here. Just trying to color it, but my coloring is not that great. It's mouse pad. Remember, there's water all through up here. Good shading. Not coloring any lines. This is walking. Let's throw some numbers here just to see what's happening. Let's imagine that this has an area of 1 meter squared, and it has a force applied of 1 Newton. Over here, our area is larger. It's 5 meters squared. One thing Pascal's principle tells us is that the pressure over here, pressure number 1, must equal pressure number 2. The pressure is transmitted equally. In order to achieve a pressure of 1, over here our pressure is 1, we can use the equation that we learned in the first lesson. Force divided by area equals pressure 1 divided by 1. The pressure is 1 on the left side. The pressure must be 1 on the right side. And the only way to achieve that is to have a force that is equal to 5. So what we see is that applying a small force over a small area, the pressure is transmitted through the fluid. If you transmit it to a larger area, you can actually multiply the force. Now this comes at a cost, you should know. You would have to move this little part down a great distance only to get a small distance moving up. But you could multiply the force a great deal and lift something that's very heavy. And that's the principle behind the hydraulic press. So I'd like to let's write this out in equation form before we do an example. So pressure 1 equals pressure 2, and pressure 1 is really force 1 divided by area 1, and that's going to equal force 2 divided by area 2. And these two ideas are Pascal's principle applied to hydraulic presses. I'd like to do an example of that, just to show you. Here's a hydraulic press here that's trying to lift a car up. Maybe it needs new brakes or something. And the example says, what force is required to lift a 9,800 Newton car that is sitting on a press with an area of 1 meter squared if the input press has an area of 0.2 meters squared? So the first thing I'd like to do is list out some values. Force 1 and area 1. And the second part of the press will have force 2 and area 2. And force 1 is unknown. That's what we want to find. That's our input force. Area 1 is the smaller part of the press, which is 0.2 meters squared. The output force is what we need to lift the car. It's 9,800 newtons. And the second area is 1 meter squared. So if we use the equation that we saw in the previous slide, force 1 divided by area 1 is force 2 divided by area 2. When we solve for force 1, we will get force 2 multiplied by area 1 divided by area 2. And I'm going to go ahead and plug the numbers. Force 1 is going to equal 9,800 multiplied by 0.2 divided by 1. And let's get an answer. Force 1 is going to equal 1,960 newtons. So if we can apply a force of 1960 newtons, we can lift this car. It's essentially multiplying our force by 5 times the amount, because the pressure is transmitted equally to the area. If you apply pressure to a small area, it will be applied equally to a larger area, giving you a larger force. So to summarize, pressure can be transmitted through a liquid in all directions. Increasing the area over which you apply the pressure can increase the force that's applied, and that is the principle behind the hydraulic press. To finish this lesson, we should do the lesson 2 quiz on the Google form, Google Classroom, and I hope that this helped give you some new information on pressure and hydraulic presses.